I'm Steve, and this is our second project for electronic workshop. So our project is based upon audio transmission design. This can be seen as a the first project, but in the first project, while the focus was on amplification, here the focus is on transmission. The medium that we have chosen for transmission is light. Here we use the input signal and we transmit it digitally. However, due to excessive light pollution, the input audio signal is prone to a lot of noise. Hence, we have to modulate it. The means of modulation that we are using is speed amplification.
Our wire consists of 6 stages. The first stage is amplification stage. We are for making initial amplification. And the second stage is triangular wave generator and comparator. We are generating triangular wave from scratch and compare it with the input signal to generate the PWM modulator. The third stage is for transmitting using light. We are choosing LED to transmit the PWM modulator signal. For receiving the signal, we are using a photodiode. And we are using the level shifter to make 8 to 5 rates. And the last stage is the power amplifier stage. For amplification, we are using 2 stages, preamp stage and main stage. Preamp stage, we are using differential amplifier. Differential amplifier because it will neglect common mode signal, which is noise. And we are using single-ended input. We are providing a input of 20 millivolts peak to peak and the frequency of 5 kilohertz sine wave. And the first one is providing a gain of 45 to 50 approximately. As you can see the yellow color sine wave with gain with peak to peak 440 millivolts. And for second stage, gain stage, we are using CE amplifier and it is providing a gain of 6. So total gain we are getting is 300 approximately. So you can see peak to peak is 2.97 volts of the green wave, which is the output from the gain stage. And we are making biasing it to 3 volts because the 3 volts bias is triangular wave we are generating is biased it to 3 volts. So we are biasing it to 3 volts by using the resistor divider.
So the next stage in our project is the triangle wave generator and the comparator. The triangle wave generator is the heart of our project. So in our project we have implemented triangle wave generator from scratch. This triangle wave generator consists of 2 parts, an integrator and a comparator. An integrator is a circuit that takes the analog input and it outputs the integer of that signal. The equations for the integrator are given as follows. Here, this point is taken as x. This acts as a virtual ground as we assume the gain of the op-amp to be infinite. And as a result, equating the currents flowing through the capacitor and the resistance, we get the output voltage in terms of the input. And we see that the derivative of the output is proportional to the input. In other words, the input is the integral of the output. And thus, this is how the integrator circuit functions. The next circuit that comes into play is the comparator. The comparator circuit can be intuitively understood as an op-amp which outputs the higher voltage. So assuming V plus to be the input voltage to the non-inverting output and V minus to the input voltage to the inverting output, the op-amp of the comparator will output V plus if V plus is greater than V minus, and will output V minus if V minus is greater than V plus. So this entire system exists in a positive feedback. The output of the comparator is fed as an input to the integrator, and the output of the integrator is fed to the input of the comparator. So in order to understand the way in which triangle wave is generated, we'll start with the comparator. Let's assume, without the loss of generalization, let us assume that the output of the comparator is V minus. Now this creates, at t is equal to 0, this creates a step function. And when this step function is fed to the input of the integrator, it gets integrated to form a ramp. When the voltage of the ramp function grows beyond the reference voltage, the comparator output switches, making it V plus. As a result, This results in a rectangular wave as an input or a pulse to the integrator, and the output of the comparator is essentially the integral of the rectangular function, which is a ramp, or in other words, a triangular function. The outputs and the plots can be seen in the DSO. Now we have designed our circuit for PWM modulation. As a result, the overall circuit is chosen so as to have high frequency, so that the carrier can accurately transmit the audio input signal. Here the triangle wave has a peak-to-peak voltage of 5 volts, and it is biased at 3 volts. And this, as you can see, is the triangular wave can be seen as the integral of the rectangular wave which was generated by the circuit. The high frequency component or the high frequency content of the triangular wave is required so that it can accurately transmit the signal without any errors. Once we have the triangle wave generated from the triangle wave generator, we use the triangle wave and the input amplified signal, and we compare them so as to produce a PWM wave. So here we have the triangle wave which we have generated from our triangle wave generator and the amplified input signal. So once we have generated the triangle wave from our triangle wave generator, we use this generated triangle wave and compare it with the amplified input signal. The comparator that we have chosen is an op-amp K319, which is high speed, which offers high speed and rail-to-rail output. Rail-to-rail output essentially means that the output pulse, digital pulse which is generated, has a low value of 0 and high value of 5 volts. This op-amp also has a frequency of 5 megahertz, hence it can easily handle the comparisons of 100 kilohertz signal, carrier wave, which is our triangle generated wave. So here we have the generated triangle wave and the input amplified signal. And this is the triangle wave generated and the pulse modulated signal. The pulse modulated signal is generated by, as I said, comparison from the triangle wave and the input signal. Wherever the input signal is higher in voltage when compared to the triangle wave, we see that the comparator outputs are high voltage, and vice versa. Wherever it is lower than the triangle wave, it generates a low output. And this is our, and here we provide a visual representation of how PWM signal works. So as you can see, wherever the input signal amplitude is lower, we see that the duty cycle or the on time of the PWM wave is less, and wherever the signal amplitude is high, we see that the duty cycle is higher, or there is more on time. And this is the basis of the PWM signal. The PWM signal modulates the message signal in terms of its duty cycle. Duty cycle is defined as the ratio of the on time and the off time of a digital pulse. So wherever the input is less than the comparator, we see that the duty cycle or the on time has decreased. Or on the other hand, wherever the message signal amplitude is higher, we see that the duty cycle is more. Now, while using PWM modulation, care has to be taken so that the input amplitude voltage does not go beyond the triangular wave voltage. So we have to ensure that the triangular wave strictly has voltage less than 3 volts. So this allows the PWM wave to have a duty cycle between the range of 25% to 75%. So this prevents there being a complete zero signal or a complete 5 volt signal throughout.